Hello and welcome to the final day of Unit 4. Today we'll be talking about Rolle's theorem and mean value theorem. So to get started, let's look at Rolle's theorem. Rolle's theorem says that if I have a function f and it's continuous on the closed interval a to b and differentiable on the open interval a to b, and that the endpoints, the value of the endpoints, f of a is equal to f of b, then there has to be a number c. Has to be a number c on the closed or the open interval a to b, such that f prime of c is equal to 0. What that means is, let's see. If I have a function here, okay, and I have some interval a to b, notice that the value of the function of a and b is equal. So f of a is equal to f of b. Then there has to exist at least one point, and in this case there are two. There's a c1 here and a c2 here, where the derivative is equal to 0. In other words, there's a horizontal tangent. In other words, there is a local max or local min. Okay? That doesn't mean that there is any certain number, but there has to be at least one. Has to be at least one. Basically, what we're saying is, if you can hold the function here, and the endpoints have the same height, then the function either goes up and comes down, and so it has to have a derivative that's equal to 0, or it goes down and comes back up, so it has to have a derivative that's equal to 0. Okay, so let's look at an example of using Rolle's theorem. So this first example says to verify first that the three hypotheses of Rolle's theorem are satisfied on the given interval, then find all values of c. Well, as you can see here, this function's a polynomial, and so 1 and 2 can be done together here. F is continuous, continuous, and differentiable on all real numbers because it's a polynomial. Therefore, continuous and differentiable on a to b. Okay. Now the third thing is where I actually have to do some work. The third thing says that the endpoints, the value of the endpoints have to be equal. So it says that f of 0, which 0, 0, 0, 5, f of 0 is 5. Let's see, f of 2 is 8 minus 12 plus 4 plus 5. That's 5. And these things are equal. Therefore, f of 0 is equal to f of 2. So the conclusion is that there must exist a value of c between 0 and 2 such that the derivative of f at those points or point is equal to 0. So let's find it. The derivative of f is 3x squared minus 6x plus 2. That doesn't factor very nicely. In fact, it doesn't factor at all. So I would have to use the quadratic formula, and when I do, I get that x is equal to 1 plus or minus 1 over the square root of 3. And 1 over the square root of 3 is larger than 1, but not more than 2. Nope, it's less than 1. Excuse me, because that's 1 over like 1.32. 1.732. The square root of 3 is 1.732. So 1 plus or minus the square root of 1 over 1.732. In fact, both of those values are between 0 and 2. So in this case, all the values of C includes all of the local max and min. It could have been the case that one of those fell outside the interval. If that was the case, then I would not include that as one of my values of C. So C is equal to 1 plus or minus 1 over the square root of 3. And at those points, at those values of C, the derivative is equal to 0. I have a critical point. And that's what Rolle's theorem guarantees. All right, so for the next example, a little critical thinking here. Let f of x equal 1 over x squared. Okay. Show that f of negative 2 is equal to f of 2. However, there's no value of C on the interval negative 2 to 2 such that f prime of C is equal to 0. So, all right, f of negative 2 is 1 over 4, and f of 2 is 1 over 4. So that part of Rolle's theorem is satisfied, right? The endpoints are the same. So there should be some value in between negative 2 and 2 where the derivative is equal to 0. But look what happens when we take the derivative of f. We get negative 2 over x cubed. Right? And negative 2 over x cubed, when is that equal to 0? Well, it's equal to 0 whenever the numerator is equal to 0. So whenever negative 2 is equal to 0, well, that can't be. That can never happen. This will never be 0. So that means there is no value of C where the derivative is equal to 0, but the endpoints have the same value. So why does this not contradict Rolle's theorem? Why does Rolle's theorem still apply here? It's still good. Well, we didn't check the first two hypotheses. We didn't check to see if the function was continuous and differentiable on the interval. And in fact, f is not continuous at x equals 0, which is in the interval negative 2 to 2. If we looked at the graph of this, at 2 I'm at a fourth, and at negative 2 I'm at a fourth. But there's no max or min there because it's not continuous. There's a place of discontinuity, therefore Rolle's theorem does not apply and is not contradicted because the original two hypotheses, the first two hypotheses, were never shown to be true. They're not true. And if the first hypotheses aren't true, then it is okay for the conclusion to be false. Okay? And not contradict the theorem. Okay. So the problem here again was that we had discontinuity on the interval. Therefore, Rolle's theorem cannot guarantee that value of C exists where the derivative of C, or the derivative of f at C is equal to 0. That cannot happen when I have discontinuity on the interval. Or differentiability on the interval. I can't guarantee it. It might exist, but I can't guarantee it. Okay, so moving on to mean value theorem. Mean value theorem and Rolle's theorem are not that different. It's just that mean value theorem is not talking about instantaneous rates of change as being 0, but instantaneous rates of change as being equal to average rates of change. Okay? So mean value theorem says that if f is continuous on the open or closed interval a to b and differentiable on the open interval a to b, then there exists a value c on the interval a to b such that the derivative of f at c is equal to the average value of f on the interval a to b. Now, what does that look like graphically? Basically, given an interval a to b, the average rate of change is represented by the slope of that secant line. Well, the mean value theorem says that if f is continuous and differentiable on that interval a to b, then there is a point between a and b where the instantaneous rate of change is equal to the average rate of change. Okay? So in other words, here's a real world example. If I'm in a car and I'm going on a long road trip, if I said that my average speed was 30 miles an hour, there has to be at least one point along that road trip where I hit 30 miles per hour at that very moment. Okay? And we'll see an example of that in the homework and later on. But let's look at a very simple example of verifying that the function meets the two hypotheses of the mean value theorem, and then finding those values of c. So here's my function. Again, it's a polynomial, so it's really easy to say. That both 1 and 2, f is continuous and differentiable on all real numbers. Therefore, f is continuous and differentiable on -1 to 1. On -1 to 1, which is the interval in question. So, find those values of c. Well, I want to first find the average rate of change. So we want f of -1 minus f of 1 divided by -1 minus 1, which is 6 minus 10 over -1 minus 1, which is 2. Positive 2. So what I'm looking for are the values of c, or the values of x, where the first derivative of f, which is 6x plus 2, what are the values of x where that is equal to 2? Well, it's when x is 0. When x is 0, that statement becomes true. So those are my values of c. Okay? Now, values of c just connects to the theorem, but that value of c is really just an x value. It's the values of x, the domain values. Okay? And 0 is between -1 and 1. Okay? Where the instantaneous rate of change is equal to the average rate of change. That's all mean value theorem is saying. Okay, so for our last example, we have a little bit of a thinker. Show that the equation x to the 5th plus 10x plus 3 equals 0 has exactly one real solution on the interval -2 to 2. So, what theorem am I going to be using? Rolle's theorem? Mean value theorem? I'm actually going to be using the intermediate value theorem. Okay? Intermediate value theorem back from Unit 1. Okay? Now, don't forget that we need to satisfy the hypotheses. The first hypothesis was that the function is continuous. Okay? It's a polynomial, therefore continuous. Okay? 2, it's a polynomial, therefore it's differentiable. Okay. And the third thing was I had to look at the endpoints. So f of -2 is -49 and f of 2 is +55. All right, well, let n equal 0. Well, n's between these guys. So f of -2 is less than n is less than f of 2. And since it's a continuous function, well, it's got to be the case that therefore, there exists at least one real number, okay, on the interval -2 to 2 such that f of c, or f of that real, so one real number c, so that that value is equal to n, which is equal to 0. So there has to be at least one, but the question asked to show that there is exactly one real solution. Well, we know that the function's differentiable on the interval, so let's look at what the derivative is. The derivative of x is 5x to the 4th, where's the function, plus 10. Regardless of the x value, the first derivative is always positive. Okay, always, I switched my W and my A. Always positive. Therefore, f, the original function, always increasing. So once it's crossed the x-axis, once it's hit this value where there's one solution, it never goes back down. So there's no possible way that it crosses the x-axis again, which in this case would mean that this has only one solution on the interval -2 to 2. In fact, it actually only has one solution on the set of all real numbers. But that's not what we were asked.